Oh, perfect. All right, sorry about that, guys. So, technical difficulties. All right, today I'm going to be talking about the 3LD. Whoop. Sorry about that. So today I'm going to be talking about the 3LD library for loudspeaker layout design. This was developed in 2006 by Dr. Florian Hollweger, and it was developed for generating 3D loudspeaker layouts, specifically for reproducing 3D audio. Now, there are a few challenges that come with reproducing 3D audio. First off, there are many different techniques of doing so. The 3LD library is optimized specifically for ambisonics and vector-based amplitude panning, but there are multiple other techniques besides that. No matter what technique you use, though, there are some universal issues to it. For one thing, 3D sound requires a mathematically regular layout, or at least as close to regular as possible, and that just means evenly spaced speakers, even angles between the speakers, etc., etc. And this is difficult to achieve because the specific techniques also have different requirements for the number of speakers and the number of channels needed to reproduce the sound. Yeah. On top of that, any 3D loudspeaker layout is going to require an associated decoder for it. You can't just plug in your iPod and start playing an MP3 on this. It won't understand that, so you need to actually write a program that will tell the audio where to go and what to do. And lastly, there are many different normalizations possible. So the 3LD library incorporates all that functionality in order to make it easier, and especially for ambisonics, that's a big deal. So my role in this process is primarily to port the code from MATLAB, the language it was originally written in, to Python. Now the reason for this is back when 3LD was written, Python was not very good for data science like this. However, since then, the NumPy module has been written, and that adds most of the functionality that MATLAB has. So we decided to port it over to Python in order to make this code more accessible and more usable for people. And then the other consideration with porting it is, since 2006, there's been a lot of research in 3D sound reproduction, especially when it comes to ambisonics. So we'd like to update the code and make sure all of that new research is reflected. And one way in particular is we are adding compatibility for a new standard that has been added recently, again in the hopes that that will improve accessibility. So what that work actually looks like, I'm going to get into right now. So on my screen here, I've got some code that we've been working on. This is the main file, I would say, for us. Yeah, so this is a collection of functions that is used for generating the initial layout. These are generally based on these polyhedron, tetrahedron, hexahedron, octahedron, etc., etc. And that's because those are mathematically regular shapes. And then additionally, if we go down here, we've got this geospheres function you can see. And then on top of that, the minimal energy configuration function. And these are two functions that allow us to take the polyhedron we got and further optimize that in order to better suit our needs. And that can be in order to add loudspeakers to a system, or to attempt to make the system more regular in terms of spacing. So yeah. Some of the difficulties with that, though, if we look here at, let's say, Geosphere. So MATLAB and Python are not written the same way at all, especially going down here. This for loop, as it's called, is something that is not reflected in the MATLAB code, which I have right here. So yeah, if we go here, this whole switch case is not something that works in Python, so this is the challenge I'm wrestling with right now, is how to figure that out. Another challenge, in MATLAB you can create an array, which is the data type that we use for storing information. And in MATLAB you can create an empty array with nothing in it, and in Python you can't. So that's been another issue we've been working on. And this all results in, if I go over here, so yeah, here we have an icosahedron that was plotted actually using that code I was showing you earlier. You can see it's a little messy right now. We still have to optimize that a bit. And a tetrahedron. So these are two of the basic shapes that we start out with, and then either using the minimal energy configuration or the geosphere functions, we can add speakers to that, or change the shape a bit to suit our purposes. So for example, with the minimal energy configuration, we'd end up with something like this. This is pretty early in the process of the minimal energy configuration. This is something that would run over and over until we achieve something that looks more like a sphere, but this is the beginning of that. And the benefit of something using a function like this is we achieve a lot of regularity, and we can specify any amount of speakers we want. We don't have to worry about the speaker numbers that we normally worry about with the other methods we use. So that's really cool. The downsides to it, though, are it's hard to build these. These are not uniform at all. So that brings us to the geospheres, which is another scheme for adding speakers to our loudspeaker layouts. And this is based on the principle of creating a shape like, say, an icosahedron, and then adding vertices in the middle of the shapes and continuing to basically subdivide the shapes until you end up with something like this. Now the benefit is that is not as regular as, say, a minimal energy configuration, but they are a lot easier to build. So yeah, I'm gonna leave it there for now because I know I went over, and thanks for watching.